Great to see you guys. So, thanks for showing up. I hope that you can stick with me here for 50 minutes. It's almost the end of the day. So, I should explain the title of this presentation. I have a colleague who a while back was hanging out on this developer forum. So it's this online place you meet and you talk about technology choice and languages and things like that. And so he was in this discussion, and people were warming up to this nice language war, right? Talk about languages. And for those who are not developers in the room, I should just explain how this works. So, one person who is intimately familiar with language A will go to this forum and proclaim that language A is the best programming language in the world, especially because it has this one little feature that most other languages, such as language B, do not have, at least not in particularly that way. And then the expected result is that some other person will join the conversation and proclaim that, well, this is all wrong, because in fact, language B is the best language in the world, especially because of this little feature it has that most other languages, for example, language A, do not have. And that's the way this works. And I don't know why it is like that, but this is how it works. So, I have this colleague who is hanging out in this forum, and we use C++ extensively at Keepit. So my colleague brings this up in the conversation. And this was a conversation about things like web services and Restful APIs and HTTP stacks and all of that good stuff. And then, of course, some participant in this forum self-confidently proclaims that, well, surely nobody would ever write a web service in C++. But that is exactly what we have done, among other things, at Keepit. So that spawned a lot of questions, and this talk is an attempt to address some of those questions, to explain to you why on earth would we do that, why would we do such a thing, and how is this working for us? Is this a good idea? So, briefly about myself. So, I was born in '76, way before the internet. I have been programming for fun for a great many years, and I've been programming for a living for something like 20-some years, in a lot of different languages. So from Fortran and C and machine code and Haskell and all of these. ML is not an abbreviation for machine learning. It's actually a language. It's not a very good language, but it is a language. So I have a master's in computer science and applied mathematics from the Technical University of Denmark. And I've been with the Keepit company from the start, so from a handful of people to more than 300 people today in 8 years. So that's been quite the journey. I work out of our Copenhagen headquarters, but we do have development offices both here in Poland and in Ukraine. And we're hiring both places too, just mentioning. So, I'm not trying to sell you anything, but I should tell you what Keepit is, just so you know what I'm on about, so this technology makes sense. Back in the day, so 20 years ago, every company would have a file server and a mail server in the basement. And you would have all your company data on that computer, and if that computer failed, then you would lose your company because now all your data is gone. That's why you would have backup, right? Now, today, people are getting rid of these servers. Nobody wants to run a file server or a mail server in the basement anymore. People move to the cloud, so G Suite or 365. There's many other services also that are moving to the cloud. But what happens in this move is you move there without the backup. So, sure, the cloud vendor, Microsoft is good at what they do. They're not just going to lose your data by accident. But if someone takes over your account, if your account gets hijacked, Microsoft can't help you get those data back. And that is where Keepit comes in. So Keepit is an independent backup service for these data that you're putting in the cloud. Which means, so what we do is we take a copy of all of this primary data that you have in the cloud. So your 365 or your Salesforce or whatever you have there, we take a copy a couple of times a day, and we store these copies in our data centers on separate infrastructure, so that if something happens to your primary data one day, we will have that copy for you. And if something happened 3 months ago, well, we will also have that copy for you. So we have customers who need to store the data for years. So some people store for 7 years, some for 20 years. We even have customers who pay us for 100 years of retention. So that's really something. That means if we mess something up today, it will be our great-grandchildren who have to solve the problem. So anyway, we believe that everything is moving to the cloud, which means, well, basically all the data that you're all sitting with in whichever job you have will eventually be stored in the cloud. So that's a lot of data that we potentially need to back up. So even if we just get, let's say, the magical 1% of the market, what's 1% of all data in the world? That's a lot. So actually it's something like, there's something like 50 zettabytes in the world, so that would be 500 exabytes, which means that if we had a storage server that would store a petabyte of data, which is a lot, we would need 500,000 of those. And this doubles every so often. So we knew when we set out to do this that we would need a very special storage architecture. So looking at available storage technologies, everyone is talking about, we have these high-capacity SSDs now that are beginning to happen, and NVMEs are really fast, and this is very interesting. In reality, though, if you need to store really enormous amounts of data on disk, it's still spinning disk. And a really interesting thing is that these disks, they rotate at 7,200 RPM. Same as they did 30 years ago. So this is a key thing in IT that really hasn't moved one bit for 30 years. This is still, well, basically the best we could do. Well, you can get faster drives, of course, but they will be much more expensive and much less economical, right? So they will be more power hungry. So we actually use these relatively low mechanical disks for this really large-scale storage. Also, I should point out that we are using actual physical computers. So we are not running out of Amazon or Azure. Briefly, we don't do what the big boys say you should do. We do what the big boys do. And there's a really good reason for that. You really can't run really large-scale storage in a public cloud if you have to pay for this, or if your customers have to pay for this. So we knew that this would be a really special problem. Right? You can go out to some hardware vendor and you can order a really large file server, but you can't really order something like, I need this 100 petabyte file server. It's not something they have, and it certainly wouldn't be cheap if they had it. And the thing is, when you write data on magnetic media, you can't expect to read it back after some time, right? So magnetic media demagnetizes. So if I write something on a hard drive today, and I try to read it back in 20 years, I probably can't. So in order to store this mind-bogglingly large amount of data, we actually need a system where we can migrate parts of the data set continually from machine to machine. As older hardware generations need to be phased out, as we retire old hardware and we get newer, more economical hardware, we need to migrate these enormous data sets. And there's just nothing on the shelves out there that can do this. And if it can, well, there's no one who can promise us that it will work in 100 years from now. So we really needed to be, well, masters in our own house here. We needed to sit down and actually build something that would do this. So storage is obviously central here, but we have a number of services around this. So when we back up your 365, there's an enormous amount of API calls we do to Microsoft, and these fail in different ways. And we have a search engine for your data. We have all sorts of things around this that we also needed to build. A common thread in all of that is that we're dealing with absolutely enormous amounts of data. And, well, it needs to work. Not just right now, not just on my computer, but this needs to work in 100 years from now. I mean, sure, we may, some code I write today may need to be rewritten within the next 100 years. I'm aware of that, but we need to basically have this ecosystem function on a very long timeline. So, therefore, we went out, found the newest, most experimental, fresh programming language to solve this problem, right? No. So, we had some things we needed from a language. And that's what I want to talk about with you guys today here. So, I group programming languages in basically 2 categories plus 1. So I have the systems programming languages. These are the languages you would use to write an operating system kernel in, or a high-performance database engine. These are languages that have very little runtime. They can run on basically anything. You can look at the code, and you can more or less see what the machine code will look like. They allow you to integrate very closely with the underlying hardware. So these are languages like C and C++ and Rust, and many others, of course. And then you have the higher level languages. So these are languages that offer the developer features that you cannot offer if you can't have a significant runtime. So it will almost always be a garbage collector in this runtime, because it will allow you to do things that you couldn't otherwise do, but, well, that has overhead. So the good ones of these languages will still be some that will allow you to integrate closely with the hardware. So you should still be able to write really efficient code, but they do have this. It comes at a cost, right? This additional functionality comes at a cost. So these would be languages like Common Lisp, which we actually also use at Keepit, or C# or Java or other such languages. And then we have the niche languages. And so I say niche languages, and if you read ahead in the slides, as I do when I look at other people's slides, you will see I put JavaScript in there. And I'm not saying a niche is small, right? JavaScript is enormously successful, but in my opinion, it's useful in a very narrow set of problem sets. That's why I put it in as a niche language. So these are like oddball languages, or just experiments that failed but then somehow stuck around. So yeah, Perl, Python, Haskell, JavaScript. We need this language to support an efficient implementation of algorithms. So when we do this storage system, we have petabytes of data, and we have the server that needs to be able to manage access to all of this data. So we need some data structures in memory on the server in order to guide when we have requests. Where does this request go? Which address on which disk should I look at to find this data that the customer is asking for? So we need accurate control over memory. It really, really matters where the bytes go. So if I have, I'll get back to the numbers later, but if I have something like 5 billion objects on one server, and maybe I will spend something like 100 bytes to keep the object ID and the address of the object. That's 500 gigabytes of RAM. That's not nothing, right? So these storage servers today, they have approximately 1 terabyte of RAM, and we're using the majority of that just for mapping out where are the objects on the server, where are the objects on the disks. So the data structure that I use for this mapping, it's absolutely essential that I understand how is this laid out in memory. Whether this is 100 bytes or 200 bytes, that means the world. Either I can use the server or I can't, right? Each 100 bytes I add, that's half a terabyte of RAM I need to put in there. So if you want to rehash this map, right, that will happen if it's a hash structure, you need to rehash it eventually. Well, rehashing 5 billion items, that's going to take time. It's really, you say, oh, but computers are fast today and we'll just add more cores. Yeah, but really? 5 billion items, that's not nothing. It will take seconds, even on a really fast computer, if it's really efficient. So if I have a CPU that is really fast at doing 64-bit integer operations, then I would like to have an implementation of my hash that uses 64-bit integer operations. I actually really care. So that completely rules out your Python, Ruby, because they're not compiled. It rules out JavaScript, because it's completely disconnected from the hardware, and rules out a lot of other languages. Especially about JavaScript. I just have to. I don't mean to be hitting completely on JavaScript here. I just need to point out. Numbers in JavaScript are floating point. I think most people don't realize how dangerous that is. Most developers are not very familiar with floating point arithmetic. So the fact that A plus B plus C is not necessarily the same as C plus B plus A. The fact that you can't really compare to 0. You can do that, but the operation doesn't make sense. You need to understand rounding errors and machine precision. Why does 1.5 round to 2, and 2.5 also rounds to 2? That's a surprise to most people. So that is just putting that in a language as the basic way of dealing with numbers. I mean, try to use them for indexing anything. Try to add 2 numbers. What does that even mean? And then, of course, arrays, which are really a hash structure, which is convenient for the niche that JavaScript serves, but super weird if you try to do something that's efficient. Imagine putting 5 billion objects in a JavaScript array and doing something with it. So anyway, these initial requirements, it means that C, C++, maybe Rust, they would be usable languages for us, but actually many others wouldn't. And then, of course, there's the tool chain, right? So this needs to work in 100 years, and yeah, maybe we'll have to rewrite the whole thing before then. But I don't want to rewrite it every 2 years. It's just, we have so much work to do. This is a lot of software we have to write. We really want to spend our time providing a valuable service to our customers. I don't want to be just re-implementing the existing software to suit a updated tool chain or a new language revision. So I want whatever language we use to work in 20 years from now. And to give that any chance of happening, I say it needs to have worked for 10 years before we start using it. I want a steady evolution of the language. I don't want any revolutions. And I think this is why when the Linux kernel, beautiful operating system kernel, modern, state-of-the-art, it's written in C. The Postgres database, an amazing piece, super advanced open source SQL server, really amazing piece of software, really, really reliable too, written in C. Why would you do that in C? Well, you would do that in C because C++ didn't exist back in the 80s or so when the Postgres database started life. So we started work in 2012, and Go and Rust, they didn't exist in 2002, so they're not interesting languages. I'm really ruling out a lot of languages here. So we run on Linux. In my opinion, anything significant on network computers happens on Linux. So the whole stack is running on Linux. I want a language that's native on Linux. It has to be, well, not necessarily born on Linux, but it has to be there natively. I don't want something that's ported as a curiosity like C#. It really needs to have a mature and supported tool chain. I need to have some evidence that there will be investment in the tool chain and the language now and in the future. So no C#, but yeah, C, C++, Rust, Go, other languages, it could work. Fortran could work. It's probably not a good idea. And when we build software like this, we have to design for failure. Every operation will and can eventually, can and will eventually fail. So when you're writing billions of objects to disk, I absolutely guarantee you that you will have failures. Disks fail in strange ways, and networks fail, and everything fails. Memory allocation fails because someone is running a larger process than you expected on your server, and now there's no more memory left. So you have to write your software to fail reliably or fail well. It's really something that's it's central, and it's easy to overlook, and it's convenient to overlook, because designing for failure is just hard work. So in languages like C and actually also Rust and Go, failures are error codes, right? Some of these languages help us check for them, some of them don't. But you have to check for error codes, you have to pass the failures back. You allocate one thing and then you have a failure, then you need to deallocate that thing before you return the failure. It's super complicated. And I'm amazed that something like Postgres can even exist, because it's really, really reliable and written in C. That's just amazing. But C++ doesn't help. C++, in my opinion, offers an improvement. So we have exceptions, and we have RAII, which, if you use it correctly, if you use it as it is intended, it actually helps you with some of these things. It doesn't mean you don't have problems, or you can have problems, but it helps you. So, in my view, this disqualifies C and Rust and Go. And then, of course, we want an enjoyable developer experience, right? We want it to be nice to write the code. But in reality, if you have functions in a language, if something is inconvenient in the language, write a function, right? You can do so much if you have functions, and Fortran had functions in 1958. So there's really not that many excuses. We should be able to structure our programs nicely so that it's nice to work with our code base, even potentially in Fortran. So C++ has meta programming, which is nice. I mean, it offers us some additional functionality. It's nothing like the Lisp macro system, which, if anyone has, I would highly recommend anyone who's a developer to learn Lisp, just for the experience with the macro system. Basically allows you to completely control the compiler, so you can write programs using the full syntax of the language to generate code for your compiler, so in the language. It's really, it allows for, basically you don't have to wait for a language steering committee to add a feature to the language, you can just add it. So object orientation was added as a library. That says something. Okay. But really, the hard part is getting the data structures right. Then the algorithms, that's just implementation, and most languages will work because they have functions. So I like the STL and RAII and exceptions and some meta programming, and I think C++ does this well. But I mean, we could use anything really. So in summary, for our language choice, it's just, given the criteria, there's just not very much to choose from. So the question here is not why we would write a web service in C++. Really, I mean, the only realistic alternative at the time was C. So the question is, what else would you do, right? What else could we have done? I mean, given the circumstances. And I would argue that today not much has changed. I know some people will say, oh, you should use Go or you should use Rust, and yeah, maybe you should. I just don't see that it's a clear, I mean, not having structured error handling, that's just a non-starter as far as I'm concerned. So, and I don't think our requirements are that special. So, meet Oscar. Oscar's in the data center. This is a picture of a rack full of servers. So I wanted to just touch briefly on the versatility of the language. So don't let anyone tell you that performance doesn't matter. It's just really, it was this, 100 bytes per object. That's half a terabyte of RAM for my objects on a server. That's not nothing. Donald Knuth was famous for saying that premature optimization is the root of all evil. You can flip that upside down and say, well, no optimization is the root of all AWS revenue. It's really, if you start your project And you say that, well, we'll just, we'll prototype this in AWS or Azure or whatever, and it's a little slow, we'll spin up some more machines. That's great. It's easy. I wouldn't blame anyone for thinking that. But once you have your prototype, once you have the first few customers on your prototype, and AWS is elastically scaling and charging your credit card, there's not going to be any time where you're going to convince the board to say, okay, let's pause for a year. We're not going to do things customers want. We're going to fix our unit costs. No. You're going to get a new investor. He's going to throw money in. Then unit cost doesn't matter. You can run at a loss. You want to grow the business. And that doesn't stay great forever. So, in Keepit, we have absolutely amazing unit cost. So it's really, a few years ago, so was it 3 or 4 years ago, we got the largest A round funding of an IT company in the history of Denmark ever. And our unit cost is a big part of why this could happen. We can actually store these ridiculous amounts of data for our customers at a competitive price and still make money. And that is something that investors like. They really like it. So it will matter for your business too. It will matter for any business. The typical hardware actually for a storage server, let me just briefly go through that. Right? So it's typically this 1 unit server with a 32 core processor with 1 terabyte of RAM. And today we have 168 22 terabyte hard drives attached to one server. So that's something like 3.5 petabytes of raw storage. We can stack these, so we can stack 4 of these servers in a rack, which gives us something like 9 petabytes of usable space for customer backup. This is consuming 8 kilowatts, which is, it sounds like a lot if it's at home, but actually for this amount of data, this amount of storage, this is actually really good. This thing weighs 1.2 tons. So when we go scout for new data center locations, this is actually something we have to talk about with the vendor. Not all floors, so these data center floors are raised floors, and not all of these floors are built for this amount of weight. So that's kind of an interesting challenge to have, that your stuff is too heavy. The 1 terabyte of RAM, that's a 3,000 to 1 ratio of RAM of disk to RAM. The industry, best practice, if you look at how much RAM should I have in my fast file server, will be 30 to 1. Now imagine that. Imagine we had gone with, let's pick this average solution and just run that quickly. We can scale this elastically. We would need 100 terabytes of RAM in each storage server. And then, RAM is cheap. But if you're getting 100 terabytes of RAM in each of your servers, trust me, it is not cheap anymore. So this has really worked out for us, and C++ has really supported what we were trying to do here. So I need to just briefly go a different direction. So I have a basement. Every basement needs a lab, and every lab needs a lab power supply. So this is a little hobby project I'm doing at home. I'm designing and building this lab power supply. And a lab power supply will have a voltage limit, and it will have a current limit. So you need 2 dials on it to control these 2 different settings. And in order to have this input, I chose to use these things called rotary encoders, which is basically a little axle that actuates 2 switches. And then you can have a little processor that looks at the signals from the switches, and then you can decode these signals, and you can find out, is the user turning the dial in the clockwise or counterclockwise. So the little square box is the processor. It's an 8-bit processor. It has 512 bytes of RAM. Not gigabytes, not megabytes, not kilobytes, but actual bytes of RAM. I'm programming this in C++ because you will notice from the picture, this is object-oriented, right? So I have two rotary encoders. They produce the same type of signal, They have the same kind of state. They need the same processing. And well, obviously, I should only write the function to decode this once. So I don't know if you can actually read the text. You don't need to read it, actually. So the big box, this is my class definition. So this is like page 1, C++, beginners, object-oriented, textbook example. I have my encoder class, which I can instantiate, and there's a function to consume these inputs and all of that. So to the left, you can see how I instantiate these two encoders in the code and call some management functions, and I can read out this data. This is all well and good. But this code, this could have run on the storage servers, right? You can't see from this code if this runs on a 1 megahertz 8-bit processor with 512 bytes of RAM, or if this runs on a 2.8 gigahertz 32-core monster with a terabyte of RAM and petabytes of disk attached. You can't see that. It's the same. I write the code the same. So the scaling here from 512 bytes to a terabyte, that's 2 billion times. So, and our brains don't really work with these numbers, right? You can't imagine what is a 2 billion times difference in size. And C++, well, you write the code the same. So maybe I wouldn't have used an 8-bit integer if I ran it on the big machine, but that's basically it. This is just unparalleled. I mean, C would do the same, but for these more, these nicer to use languages, I mean, Java, for example, we use a state-of-the-art security monitoring solution written in Java. The vendor says you can never put more than 32 gigabytes of memory in a node. So you need a lot of nodes, and you need expensive licenses for all of them, of course. How convenient. The smallest system that would run Java, I don't know, half a gig of memory maybe, a quarter of a gig. Not sure. If you need to do anything significant, you would be hard-pressed. That's like 64 times from the smallest to the largest system, and that's stretching it. We are not even stretching it at 2 billion times. Right? I could probably run this with 200 bytes of RAM. And the 1 terabyte in the big machines, that's not the limit. We could go way higher. And C++ would allow us to write code that would use this super efficiently, completely use the entire power of the hardware. So just quickly, the rest of the stack, we have an HTTP stack that we did write in C++. And yeah, we use Restful APIs over HTTP, so all of these storage requests that are coming in and out with these billions of customer objects, this is all over a Restful API. And yeah, there's one line of code to instantiate a web server, because why would you need more than a line of code to instantiate a web server, right? So this isn't difficult in C++. And if it is, well, you should write the code better, right? So we have an XML stack also. So we use XML in our APIs. That's a topic for another day. In XML, you have this syntax called RNC for describing the schema. So this will describe the structure of a document. So here I have a search document. I have a filter specification. This is just a notation for writing schemas. It's not code as such. And then we used C++ metaprogramming to make a parser generator for this. So it looks a little hairy on screen, I get that. But it's sort of the RNC syntax, just slightly differently. This will use C++ metaprogramming to generate a really efficient parser which will take all of these. It will pass an XML document, and it will validate that it lives up to the schema, and it will throw an exception if it doesn't. And then it will decode all of these different elements of all of these types that we specify. So if I say something is a Boolean, and it doesn't pass like a Boolean, it will throw an exception. So this is really amazing for things that are, where you need reliability in your code. You really want When someone sends you a document and they put an integer instead of a boolean in a field, or they're trying to escape something, or it is just really, really nice to have a validating parser that will just throw if something doesn't live up to specification. So it makes it simple to be safe. Now, we have a bunch of other services in our stack. So we have API front-ends, application servers, and a search engine. Actually, the search engine, that was an interesting story. We started out like everyone else does. When you need a search engine, you get Elasticsearch, and then you fire that up, and you start loading data into it. And you have these 32 gigabyte per node limitations, and you work around that, and you spin up more servers. We couldn't make this thing scale. We have so many more writes than we have reads. Elasticsearch is pretty good at searching. It's not very good at updating, and we have almost only updates. So we started this side project. We did a Plan B project where we wrote a search engine from scratch in C++. And not long after having done the prototype of that, we scrapped the Elastic completely. And to this day, our search engine is still called Plan B Search. So in Keepit, we have a code split. So like I said, we do use, so 81% of our code base is C++, 16% is Common Lisp. So we use Common Lisp for these other backend, we use it in two ways actually. We use it for some of these backend functions that were initially just a mess of different shell scripts, and we had Perl, and we had 5 different versions of Python, as you have, and all of that, right? So someone needed to, we need to send a welcome message to a customer when a customer signs up. So someone did a script for that, and then now we need to send this reset password message, and someone picked a different language and did a script for that. And whenever someone needed to fix something, we had to first rewrite what was written and then do the fix. So we stopped that and collected all of this in a Lisp system. So we used Common Lisp initially for these business support functions like messaging, resource accounting, billing, things like that. We have a different, maybe less traditional use of Common Lisp also. So when we do these backups of customer data sets, we have all of the email, for example, we have all of the chat messages from all the employees in an entire company. When we complete a backup, we actually have a Lisp system that reads through all of your email. It will open the email up and it will extract metadata. So things like subject and to and from addresses. It will pass these emails and it will extract the metadata. And then it will transform this and send it to the search engine, so that when a customer loses some important email, they can do this search. So they can say, through all of my backup history, I would like to see which mails I have with a subject that looks like this. And then we can do the search in the search engine, and we can show you the results that you had this mail, you deleted it 3 months ago, so here it is, and you can download it and restore it. So we use Common Lisp for this metadata extraction and import. So this is a multi-threaded traversal of this enormous data set that is a customer's backup data. And most of the memory management happens outside of the garbage collector. We just use a really powerful language to implement in a safe way this rather complicated piece of logic. So that's a less traditional use of Common Lisp. And I hear you say, surely nobody would write a web service in Common Lisp. But so we did that too. We had to, everything is RESTful APIs internally, so obviously we needed a stack for that as well. So, let me briefly run through the recap this for you. How has this been working out for us? Well, first of all, having multiple languages suck. It's bad to have to write an HTTP stack in both Common Lisp and C++. It would have been nicer to only have it in one language. And we also have, connection pools. We have the XML stack. There's so many things that you need to duplicate, and that's bad. But on the other hand, the reason we have Common Lisp is before we had Perl, Bash, Python 2.7, Python 2.75, Python 3, and it was so. In a sense, we're lucky to have only two languages. So I'm very happy that we have only two languages. Those two languages complement each other. Right? So the macro system in Lisp is it makes Lisp the most powerful language on the planet by far. I mean, no comparison. Since you can just implement features. It's not about comparing feature lists, because there's no feature another language can have that you couldn't just write as a library for Common Lisp. So it's really not a competition. But of course, having the runtime and I mean, there are just practical things around the tool chain that you wouldn't want to write your operating system kernel in Common Lisp. And yeah, we wouldn't want to write our storage system in Common Lisp. So C++ and Common Lisp complement each other really well. They're just uses where it's often really clear where something belongs. So that's nice. So my advice would be, if you want to have more than one language, then at least make sure they solve different problems. Of course, we also use JavaScript on the front end, obviously, because what else would you do? Recruitment for various languages, that's something we get asked a lot. So people tend to say that, it's so difficult recruiting for C++ or Common Lisp because it would be so much easier if you used web technologies. And then you say, okay, but I need some JavaScript developers too. And then all of a sudden, that's also difficult. Right? It's just, in my experience, finding the right people is difficult regardless of language. In my experience, I wouldn't say it's more difficult to find a Lisp developer than it is to find a JavaScript developer. Of course, if you want to find any JavaScript developer, then that's easier than finding any Lisp developer. But if you want to find the right JavaScript developer, that is just as difficult as finding the right Lisp developer or the right C++ developer. So from a hiring standpoint, I think that these three languages, it's sort of, I mean, finding great people is just hard work. Doesn't really depend on the language. So if any of you are not through university, I just have a little bit of advice I just wanted to give, right? So consider formal education. I mean, consider getting a computer science curriculum at a university. I know some super smart people who don't have that, but it really helps to have a foundation. I would advise that you learn more than one language, and you actually go through the pain of writing something significant in it. I mean, fail multiple times, right? Write something big and realize it was stupid, and then rewrite it and fail again. Learn how these things can complement each other. Learn why, when someone says language A is the best language in the world because it has this one feature that language B doesn't have, then be the one who knows that there's a little more to it than that, right? It's not that simple in the real world. Make sure that you learn a systems programming language. So C or C++ or any one of these really low-level ones. Make sure that you can make a 64-bit integer and add it to another 64-bit integer and know what machine code comes out of that and why. And then I would always recommend that you learn Common Lisp, no matter if you ever need to write anything in it, but having seen what's on the other side, knowing what's possible and what you can do with the language is just, it helped me. So I learned Common Lisp very late in my career. I think it should be criminal for universities to have a computer science curriculum and not teach the students Common Lisp. But I learned it late in my career, and it has just been eye-opening, and I have definitely changed how I use other languages as a result of that, in a positive way. So And then, of course, I would advise that you learn JavaScript. So, because I mean, I could speak for another 50 minutes on why that's in so many ways a terrible language, but it just solves so many really, really important problems. And you can make the best backend in the world. If you can't show it to anyone, doesn't matter. And to show it to anyone, you need to use JavaScript. So that's the end of it. Any questions? Yes.
Okay, thank you. 2 questions. First one, hardware question. You mentioned that you are using spinning disks for backups rather than tapes.
Yes.
Why?
So we did use tapes. A great question, by the way. So we did the math, right? We looked this up and we saw we need to store an obscene amount of data. How do we do this most economically? So we decided, okay, tapes is the cheapest option. So the first version of Keepit that we launched was based on tape. So we didn't want to write the software to manage a tape library. So we took an off-the-shelf solution for that, and then we wrote a backend that would interface with that. And then we wrote some client software also. The thing is with tape, so a tape that's idle doesn't consume power. So that's great when you have enormous amounts of data. You regularly need to move data around on the tapes, which means you need a large number of drives standing by, and they will regularly be moving data. So they get worn. So you have both wear on the tapes and wear on the drives. So there's a maintenance cost here. Your hardware is going to need ongoing maintenance, so you need these service subscriptions. So we have one of the largest tape libraries in Denmark, and maybe that doesn't say a lot, but we have a really large, walk-in sized tape library with a robot in it that picks tapes. And the thing is, once you buy into, let's say, an IBM tape library, you're never getting out of an IBM tape library. It's just, you can't switch vendors, right? The software won't work. Nothing is interoperable. You're just stuck with one vendor, and they just have you. If they want to grow the revenue 20%, they jack your price up 20%. And they did that. And they seriously told us. It's like, we decided revenue should grow 6% this year. So now your price is 6% higher. It's like, what are we getting? Or nothing. So they have you completely, and there's nothing you can do. And then as technology evolves, so tape drives actually evolve too in capacity. So you get higher capacity tapes and higher capacity tape drives. But once you have your library full of one generation of tapes, then you need to decide, do I want to buy from scratch a new library with the newer generation tapes? Or do I want to start replacing some of my drives with larger capacity drives that are not backwards compatible with the old ones necessarily, at least only for 2 generations, and then start replacing tapes with newer? It just gets the logistics in this just makes it so that initially it looks great. But over time, it's just the hassle and it's terrible. And then finally, customer goes in and says, I want this document now. And then we show a spinner saying, yeah, let us get it for you. And then 5 minutes later, okay, we have it. That's not what people expect in the cloud. And that's why we said, okay, we need to fundamentally rethink this. I want someone to be able to go in, look at the backup history, say, I found this document 8 years old. I want this now. And then they click it and they get it. And that's what we managed to get. So yeah, in a sense, it seems wasteful, but these are really high capacity drives. The overall power consumption is really low compared to the amount of storage we have. And it is the cheaper solution, oddly.
Okay, I see there's a very scary beast over here, so does anyone else have any questions?
Hi, thanks for the talk. I was wondering, because you said that you had to have some error handling, and I was wondering how do you handle allocation errors, and is it more sophisticated than just terminating the process?
Yes. So and great question. So yes. So when we have these, when the code is written so that it is exception safe, what happens is that where we get the allocation failure, we will throw, and then it will come back to whatever handler it makes. Whatever handler is the first to catch it. So what happens on our API front ends, for example, is you make an HTTP request, and then so I know because I've seen this particular case in production that for one reason or another we're running out of memory on an API front end. Someone makes a request, it triggers all the way down, then deep down in the XML stack or whatever, some allocation fails. This rewinds all the way back to the top level request handler, and it will then it will generate a 500 error and send you a proper, well-formed HTTP 500 status code back saying, no, I couldn't serve your request. And then, of course, internally in our logs, we will log a little more detail, like, we're actually out of memory. So ops will see that. So, so this actually works. And this was not a special case we coded for. This is just the result of actually using RAII and exceptions and writing exception-safe code. And that is sometimes hard to do, but it's possible, and it actually works this nice.
So if we still have time, a software question this time, especially regarding the duplication of stacks. You mentioned that you need to write a lot of software in Lisp, then the same software in C++. Have you actually evaluated CLASP, the Common Lisp implementation that solves the problem of making it possible at all to interface with C++ code? So that in theory, from Lisp you can jump to C++ code, call it, have it return in a more or less smooth way without using FFI or something else.
Yeah. So we haven't evaluated it. Well, I haven't evaluated, and I believe that others also haven't evaluated. I saw a presentation about it. I thought this sounds amazing. I asked some of my colleagues to look at it, and they had already looked at it, and they had some really good comments actually about that. So I think it's not as simple as, I mean, there's some practical implications that just makes it not the obvious choice for us. I don't remember what they were. I'm sorry, but it's also the concept. I mean, when I write something in Lisp, I mean, I want to use the power of the language. I want to have the guarantees that the language gives me, and then calling out to foreign code is kind of, it defies the point of using Lisp in the first place. So we do have a couple of C functions that we call from Lisp, but it's a bare minimum, and I really wanted to just get away completely from that. So if someone wants to write an open SSL implementation purely in Common Lisp, then I would be very interested. So. We also way over time. Thank you all.